Silent supersonic flight sounds impossible, yet acoustic metamaterials are claimed to make it achievable today. Let's examine physically. Supersonic aircraft generate shock waves because information cannot propagate upstream beyond Mach 1 in compressible aerodynamic flow regimes. Those shock waves merge, forming coherent pressure disturbances that propagate through the atmosphere and eventually reach the ground below. A sonic boom is not ordinary sound or conventional noise. It is a nonlinear atmospheric shock phenomenon. As multiple shocks coalesce during propagation, observers detect a characteristic N-wave pressure time history signature pattern. Peak overpressure depends on Mach number, aircraft length, total weight, and spatial lift distribution characteristics. Crucially, sonic booms are dominated by very low-frequency acoustic components rather than high-frequency content. Typical dominant frequencies range approximately between 1 and 100 Hz at ground level. That corresponds to acoustic wavelengths measured in tens to several hundreds of meters. Already, a fundamental scale mismatch problem is beginning to emerge clearly. Now consider acoustic metamaterials carefully and what they are physically designed to accomplish. Metamaterials manipulate effective density and bulk modulus using engineered subwavelength resonant internal structural architectures. They create acoustic bandgaps, preventing wave propagation within specifically tuned frequency intervals. Most laboratory demonstrations operate at kilohertz frequencies, occasionally lower, but rarely within infrasonic regimes. Their unit cells are typically centimeters or smaller in characteristic geometric dimension. They excel at attenuating structural vibration and mid-frequency airborne sound efficiently. In aerospace applications, related concepts appear within advanced turbofan engine acoustic liner technologies. Those liners mitigate tonal and broadband fan noise inside nacelles effectively. However, a sonic boom propagates externally through kilometers of atmosphere surrounding the aircraft. This distinction between internal attenuation and external shock propagation is fundamentally critical. Let's now compare the characteristic physical scales quantitatively and rigorously. At 10 Hz, acoustic wavelength in standard air approaches approximately 34 meters. At 1 Hz, wavelength exceeds 300 meters in atmospheric conditions. An aircraft fuselage skin panel is certainly not hundreds of meters thick. To create a bandgap at those frequencies, resonators must approach comparable characteristic length scales. Otherwise, effective medium approximations break down severely and predictive capability collapses. Now consider the energy transport associated with a propagating sonic boom. It represents a coherent pressure impulse distributed across very large atmospheric volumes. Attenuating that externally would require substantial impedance interaction with the advancing shock wave front. A thin structural fuselage layer cannot absorb kilometer-scale shock energy. Could distributed metamaterial surfaces reshape the boom before ground impact instead? Only if they alter global pressure distribution prior to nonlinear shock formation processes. But shock formation depends primarily on aircraft geometry and lift distribution characteristics. That shifts the engineering solution toward aerodynamic shaping rather than acoustic absorption mechanisms. This philosophy underpins current low-boom demonstrator development programs worldwide. Consider the X-59 QSST experimental aircraft specifically designed for low-boom research missions. Developed by NASA in partnership with Lockheed Martin for advanced supersonic studies. Its elongated nose and distributed volume carefully tailor shock strength progressively. Instead of a sharp explosive crack, observers hear a softer aerodynamic thump. No external metamaterial blanket is required for that outcome. Aerodynamic shaping modifies near-field pressure before nonlinear shock coalescence occurs. Mission profile adjustments further reduce ground signature intensity significantly. Higher cruise altitude increases propagation distance and smooths waveform pressure gradients. Lower Mach numbers inherently reduce shock strength and overpressure magnitude. These strategies act directly at the disturbance source location. Metamaterials would attempt acting after wave formation, externally within atmosphere. Engineering practice typically favors source control over downstream mitigation strategies, especially when acoustic wavelength vastly exceeds structural characteristic dimensions involved. So are acoustic metamaterials entirely useless for supersonic aviation applications? The answer requires nuance rather than simplistic dismissal. They remain promising for internal cabin noise attenuation technologies. They may significantly enhance turbomachinery acoustic liner performance systems. They could tailor aeroelastic structural response through dynamic impedance control. However, primary sonic boom mitigation demands aerodynamic control authority. Physics ultimately dictates where each technology operates most effectively. Frequency content, spatial scale, and transported energy determine feasibility boundaries. When those parameters mismatch, conceptual appeal collapses under dimensional analysis scrutiny. Silent supersonic flight is therefore not an acoustic absorption challenge. It is fundamentally a pressure distribution and shock management challenge. If silence ever emerges, it will be aerodynamically shaped, not acoustically absorbed.